Today, we'll be talking about central limit theorem for Bernoulli trials, exploring conversions to law of large number and CLT. We'll also discuss their uniform extensions via Glevenko-Cantel and Donsko's theorem, and introduce the concept of Brownian bridge. Introduction. Now let's get to it. Let's talk about introduction of central limit theorem for average Bernoulli trials. The central limit theorem applies to average Bernoulli trials with the variance changing. To make a uniform statement, consider conversion of Fn to F using law of large numbers CLT for fixed t. Law of large numbers Fn will converge to F as surely when n goes to infinity, and as square root of n times Fn minus F will definitely converge to a normal distribution with mean 0 and variance ft and 1 minus ft. Now let's talk about uniform statement theorems. Can you tell me what would be the uniform statement theorems related to the law of large numbers and CLT? Think about a few seconds. It says that law of large number uniformly becomes Glevenko-Cantel theorem, and CLT, central limit theorem, uniformly becomes Donsko's theorem. Now let's focus on Donsko's theorem in this presentation. Donsko's theorem states that for a sequence of empirical distribution functions, that is this one, the supremum of t that belongs to R times square root of n will definitely converge to a supremum of Bt, Brownian bridge, of time t as n goes to infinity, where B is a uniform distribution between 0 and 1. Now let's understand Brownian bridge for a few seconds. Before I say what Brownian bridge is, let's think about what Brownian bridge means from what you already know, may know. Brownian motion starts at 0 with tiny increments and a stochastic process indexed by t. Distribution of Bt in Brownian motion is n, normal distribution with mean 0 and t. It varies increasing linearly with time. The covariance between Bt and Bt dash describes a Brownian motion. Stochastic process and conversions. Let's talk about that. A stochastic process is necessary to describe random variable indexed by t and their worst possible values. The variance of Fn minus F as t goes to negative infinity is 0, and Ft is 0 as t is equal to infinity, when t is equal to infinity. As t tends to infinity, Ft equals to 1, resulting in 0 variance. Conditioning the Brownian motion. The condition, the Brownian motion to return to 0 at time 1, resulting in Brownian bridge. A Brownian motion, what is Brownian bridge again? Think about it. A Brownian bridge is something a Brownian motion conditioned to return to 0 at time 1 with variance following a pattern from 0 to 1. So, let's talk about uniform central limit theorem. Donsko's theorem can be viewed as a uniform central limit theorem. The distribution of Brownian bridge is independent of any specific f and is purely Gaussian. No matter the averaging and taking the supremum, the end result is Brownian bridge. Now, let's talk about summary. Let's summarize what we learned today. In summary, central limit theorem for Bernoulli trial shows changing variance by sample size. Fn converges to F using law of large number and CLT for fixed T. Gleevenko-Cantillon and Danska's theorem expand its uniformly. Danska's theorem, introducing Brownian proofs, provides a uniform central limit theorem with purely Gaussian distribution. That's all for today. I will see you next learning session. Thank you so much and have a nice day.